So now we know about the recursive descent algorithm, and it's a very popular algorithm used in many compilers, primarily because of its simplicity. However, recursive descent parsing has a big major drawback, and that drawback is called left recursion. Some grammars exhibit left recursion, and so if a grammar exhibits left recursion, recursive descent parsing cannot be used to parse that grammar. To see what is left recursion, consider this example grammar. In this grammar, there's one non-terminal S and there are two productions. In one production, it produces SA, and in another production, it produces B. Notice that this grammar produces strings of the type either it will produce the single character B, or it will produce BA, or BAA, or so on and so on, right? So it could produce B followed by any number of A's. Now, if I was to implement recursive descent parsing for this grammar, my functions would look something like the following. For the first production, I would define a function called S1, and that is going to chain the function objects like we discussed last time. However, the first function it's going to call is going to be the function S. Right? I'm writing it slightly differently in this slide. I'm kind of omitting some details related to function object chaining. But basically what happens is S1 first calls S, and then it checks whether the remaining string matches A or not. And so S1 is calling S without consuming any token. And if you look at S is going to again call S1 without consuming any token. If for example, if S1 was the first production to be tried, then S would immediately call S1. Even if S1 was the second production or the third production to be tried, before S1 is called, the next pointer would be reset to the beginning before calling S1. And so S1 calls S without consuming any token, and S calls S1 without consuming any token. And so now we have an infinite loop that keeps recursing mutually without consuming any token. And this is basically going into an infinite loop. Another way to look at this problem is that the grammar, if you look at the grammar, the way if I try to derive any string of tokens from this grammar, I'm really deriving the string right to left. For example, I would say, let's say I was to derive BAA, then I would first say, let me derive SA. So I first derive the rightmost character, then I derive the second rightmost character, and finally I derive the first character. So in other words, the derivations are happening right to left. On the other hand, the parsing algorithm, recursive descent parsing algorithm, is kind of trying to parse or reduce the string left to right. And so this is a conflict, and that's why we are ending up with an infinite left recursion problem. Okay, so the grammar produces strings right to left, and this is the problem with this grammar, and that's why recursive descent parsing will not work on this grammar. However, it turns out that if there is a grammar that produces strings right to left, it is possible to convert it to a grammar such that it starts producing strings left to right and yet accepts exactly the same language as the original grammar. So to see that with an example, I could rewrite this grammar that S produces SA or B as follows. I introduce a new non-terminal S prime, and I say S produces B S prime, and then S prime produces A S prime or epsilon, which basically indicates that S prime produces a string of A's, and S produces B followed by S prime, which means B followed by a string of A's. And this is exactly the set of strings that the original grammar accepted. However, there's an important difference between the second grammar and the first grammar. While the first grammar would produce strings right to left or derive strings right to left, the second grammar derives strings left to right. For example, the first character that it derives is B, and then it derives the next A, and so on until it reaches the last A. Okay, and this particular grammar does not have the left recursion problem and can be parsed using a recursive descent parser, because S is going to consume a token before calling S prime, and S prime is also going to consume a token before calling itself. So this problem avoids left recursion. Okay. More generally, if I have a grammar that looks like the following, that is left recursive. For example, S produces S alpha 1, where alpha 1 is some string of terminals and non-terminals. Similarly, it can produce S alpha 2, S alpha n. The common thing among all these productions is that the first component of the RHS is the same non-terminal S, and so it's a left recursive grammar. And then maybe it has some other productions, beta 1, beta 2, beta m, which do not involve S as its first component. And such a grammar can always be rewritten to the following, and this is just a generalization of the example that we saw in the previous slide. We define another non-terminal S prime, and we say S produces beta 1 S prime, or beta 2 S prime, or beta m S primes, because that's what the first part of this grammar will produce. And then S prime produces one or more strings of either alpha 1, a string of one or more alpha 1, alpha 2, dot 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 alpha n. And so that's what the second non-terminal produces here. All right. So any grammar that has this form, the first form, which is left recursive, can be converted to the second form, which is not left recursive. Notice that the second form is not left recursive because some tokens are being consumed before there's a loop in the recursive call stack. All right. Here's another example of left recursion. So left recursion need not necessarily be manifested as shown in the examples earlier, which means that a production from S produces S as the first component in the RHS. It could also be because of transitive productions. For example, in this example, S produces A, small a, or D, and A produces SB. All right. And so in this case, S does not directly produce S, but S produces A and A produces S, and we have the same left recursion problem in this example as well, because S after one or more derivations does produce S as the first, as the leftmost non-terminal in the derivation tree, and a string in the derivation in the derivation, and so if I was to implement this using recursive descent parsing, the function that implements S would end up calling itself without consuming any token, and we will end up in an infinite loop. While there exists a general algorithm to tackle this type of left recursion also, we already saw an example of how to tackle left recursion for certain patterns of grammars in previous slide. Even for more kind of subtle forms of left recursion, as shown in this slide, there exist algorithms to convert those grammars into non-left recursive grammars automatically. And we are not going to go through such algorithms in this course. Also, I should point out that even though there exist automatic ways to convert left recursive grammars to non-left recursive grammars, the actions associated with every reduction. So while we have been talking about mainly whether a string is accepted by a context-free grammar or not, typically whenever there's at every step of the derivation, we need to do some kind of actions, as we're going to see later when we discuss code generation. And so when we transform the grammar automatically, it becomes difficult to figure out which action should go at where. And so such things become slightly more difficult. Instead of trying to solve the problem of left recursion using automated algorithms to transform the grammar, we're going to discuss some other parsing algorithms that do not have this left recursion problem. To summarize, recursive descent parsing is a simple and general parsing strategy. However, it is important that left recursion is eliminated. It can either be eliminated automatically or it can be eliminated manually. And in fact, in spite of this problem of left recursion, recursive descent parsing is pretty popular. It is used in many compilers, including GCC, because of its speed. In your assignments, we ask you to look at the tiny CC compiler, and even that is using a hand-coded implementation of a recursive descent parsing.